Hello everyone, welcome to the third live session for this course. We'll be discussing some of the questions that were asked by all of you on the Excel sheet that was circulated on the Google form. And along with that, please do send us your questions in the chat box and we can also take them one by one. I have with me Vishal here, who is one of the TA for this course, and he'll be taking some of the questions and I'll trying to answer them as we go along. Okay, so I guess we will start. There's already one question maybe in the chat box. We can start with that.
Sure. So the first question that we are going to start with today is one of the users has asked, please explain the major difference between step reaction and chain reaction.
Okay, so let me just quickly shift to the board. And so basically step versus chain. And so in generally in step reaction you have monomers. So these are again both of these are in context to polymerization. And what happens is in step reaction you have monomers. So let's say each of these monomers are represented by these circles. And so you, of course you have a monomer that reacts with another monomer to form a dimer. So there's only one way for this can happen. A monomer has to react with another monomer. Now if you have to form a trimer, again it's the same process. It will have to a dimer will have to react to form a trimer. But then as you further go on, this changes, right? Because now if you have to form a tetramer, then there can be several cases. You can have a trimer that reacts with a monomer. You can have two dimers reacting with each other. And so the reaction is actually quite fast. The monomer is consumed very quickly. And given that most of the time the affinities are quite similar for these reactions, you end up forming maybe 100 chains each containing on an average maybe, I mean these are random numbers I'm saying here, but each containing maybe let's say 20 monomers, right? As now what happens in chain reaction, so chain reaction generally requires some kind of an initiator, so let's say that's represented by I, and so initiator is activated or initiator itself activates the reaction, and so the initiator goes ahead and reacts with a monomer, and now only on this initiated reaction can this reaction proceed. So this will be reacting like this. So all the other monomers are just lying and waiting for an initiator chain to come and react to them. So that way the reaction is a bit slow because it's not like all of them can react with each other, which was happening in the step reaction. So you can then control how much of monomers you want. For example, if I only put let's say 5 initiators at the start, and of course initially I had what about 100 into 20, so about 2000 monomers that were present in the reaction. So if I only have 5 initiators, then only these chains can grow, and then their growth will be quite uniform, and so will basically form polymers that would have a molecular weight or that will have monomer units of basically 400 monomer units. So you can get a very long polymers by this method. It is a bit slow, so this is slow, this is fast, but this is much more controlled, whereas in this the control is low. So that's basically the major difference with all this. Okay, let's get back.
I think regarding the exam, we can come at the end.
Sure,
I'll start with the forum questions.
Whichever questions you want to take first.
So the first question from the Google form that we had circulated is, how does bacteria adhere to biomaterial if the surface is hydrophobic?
Okay, so I mean, see what happens is there are all kinds of proteins and receptors that are involved in this reaction. So if we have a surface which is hydrophobic, that would mean that the bacteria will have its own proteins that will be secreting or will be present on the cell surface of the bacteria. So those proteins will then adsorb on that surface. We know hydrophobic surfaces adsorb a lot more protein than compared to hydrophilic surfaces. And so on hydrophobic surfaces, generally you'll find that the bacterial colonization is faster and much more rampant than as compared to the hydrophilic surface. But the whole process eventually is that some of the proteins that are present on the bacterial surface or secreted by bacteria go and attach to that surface. And once that happens, then the bacteria can then bind and start to grow, proliferate, eventually forms biofilms.
So the second question has two parts basically. The first part is how does water contact angle help in non-adherence of bacteria? And the second part is that the student has asked to explain a brief about the plasma treatment of this.
Okay, so both of them related questions. So maybe I'll just go quickly to the board again. Okay, so so again, you have a surface which may have a certain hydrophobicity, and the water contact angle is nothing but the measure of how much is the hydrophobicity of that surface. So if I have to, let's say here's a surface. This is a thick line. Let's change this. Okay, here's a surface, and now if I have to measure the water contact angle, what I'm going to do is I'm going to just put a water droplet here. So the water droplet can spread quite a lot, or the water droplet could be like this, or the water droplet could be like this. That depends on how much the water wants to interact with the surface, right? If the surface is very hydrophilic, then the water will tend to spread out because it wants to have a larger contact area with the surface. And to measure the water contact angle, all you have to do is you have to measure this tangential angle at the edge of this droplet, right? So if you do that, let's say this is theta, so this theta will then define how hydrophilic and hydrophobic it is. So water contact angle is just a measure. It doesn't really help in adherence of proteins and all, but it can help you sort of make a rational guess as to how much proteins will adsorb to it, or whether more or less proteins will adsorb to it. So we know that hydrophilic surfaces tend to absorb less water. That's because a protein which is already in water is already interacting with a lot of water molecules, and it's fairly happy here, and so it may not want to leave these water molecules to interact with another hydrophilic surface. So in general, on a hydrophilic surface, most proteins don't adsorb much, but then if the surface is hydrophobic, so this angle is now increasing. In those cases, the inner domains also want to interact with those surfaces, and that's when the conformation change happens. The proteins tend to adsorb. So that's the whole concept between the plasma serum adsorption and the water contact angle. The second part of your question, could you repeat?
The plasma treatment.
Okay, yeah. So what does plasma treatment do? So basically, it depends on what gas you are using. For example, you are using oxygen gas as plasma. So you're basically bombarding this surface with oxygen gas, which is going to cause oxidation of the surface and will create these hydroxyl groups on the surface. Now these hydroxyl groups, of course, are hydrophilic because they have oxygen there, electronegative, conform hydrogen bonding. So essentially what you will end up doing is pushing the surface to become more hydrophilic, having a lower water contact angle, and hence absorbing less protein. So that's the main function. So you could use other gases also. You don't have to use oxygen only. You can use chloride, you can use ammonia, so all kinds of gases, whichever are hydrophilic will end up making the surface more hydrophilic.
So the next question is, what is the role of secondary and tertiary amines in proton sponge effect?
Okay, let's go back to the thing here. Okay, so in terms of the proton sponge effect, if I quickly recap, what is happening in the proton sponge effect? There is an endosome which is carrying your particle, and that particle. So let's say here's a large cell, here's an endosome, and within this endosome there is a particle. Now the endosomes want to maintain a low pH, so they start with a pH of 7 and it progressively drops down all the way to 3 or 4. Um, and that happens because more and more H plus ions are being pumped in. And these H plus ions, when they are present in these endosomes, they are responsible for lower pH there. Now, if I have tertiary and secondary amines, so basically I have NH, or um, I have these tertiary amines. So all of these nitrogens have these lone pairs that it can use to ionize itself and become NH2 positive or NH positive, and once they do that, they're basically absorbing all these H plus ions that the cells were pumping in. Now the cells, when they pump in H plus ion, they're also pumping in other ions such as chloride and whatever the cell may need, and so also to maintain the charge balance. Now you are absorbing H plus and cell wants to drop the pH, so it continues to pump the H plus ions. So eventually what happens is you have much higher concentration of chloride ions that are present here, and that causes osmotic imbalance. So the water then goes in to maintain this osmotic balance, and eventually there is a capacity to which this endosome can swell, and eventually it just bursts, releasing the particle out. So that's the basic role of the secondary and tertiary amine.
The next question is regarding the use of nitinol wire in gastric residence system. So the research says that when we use some kind of a nitinol wire for drug delivery in gastric system, the drug can be released for a duration of more than 1 month. So the student is asking whether such kind of a wire is a because it's a foreign object to the body, would it cause an immune response?
Okay, that's a good question. So yes, you are right that that wire is going to sit in the stomach for about a month, and there are chances that there could be immune response. However, we also have to look at what site this is going on. So the stomach has a very low pH, and it is a very dynamic place where the food is coming in, the fluids are coming in, they're going out through the intestine and all. So yes, the thing is that there are hardly any live cells that are present in your stomach. So even if nitinol wire may be immunogenic, the immune cells are not even there. They can't survive at that low pH. And so eventually what happens is that wire continues to be there. There's not much cells or even for that matter proteins that are being secreted in the surrounding to cause inflammation. So that is not a major concern in that particular case. So yeah, they can get away with that.
The next question is, please explain liposomal drug delivery in brief.
Okay, so in brief, okay, let me maybe go back to the board again. So liposomes are one of the most widely used systems, especially clinically. They were one of the very first generation of particles that made it to the clinics. Quite successful actually, and quite safe as well. So what basically is a liposome? So you have these lipid bilayers similar to what we have on a cell membrane, and you basically make a vesicle out of it. So all of this is lipid bilayer, and then you have this inner space in which there's water, or any buffer that you may have used. You have these all of this region is hydrophobic space, and all of this region is hydrophilic space. So you can use the system to then, if you have a hydrophobic drug, because it doesn't want to interact with water here or the water here, it will preferentially go and get encapsulated in this region. And this is what can be used then eventually to encapsulate this drug and slowly release. And similarly, if you have a hydrophilic drug, you can put it here, and because there are all these hydrophobic domains here, the drug will remain entrapped. And slowly, I mean, some of the drug, depending on the solubility in water, will start to come out over time. So you get a very sustained release system, which will release the drug over a period of maybe few hours to days, depending on what your system is. And that is in a nutshell what is used. Now you can control the size here. So these can be as low as 100 nanometer, or these can be as high as 10 micron. So if that is the case, then depending on the application, you can load a lot of different types of drugs, and they'll release over time. You can use the EPR effect for cancer drug delivery with this 100 nanometer size particle. And similarly, if you want to create a depot at some place, you can inject this larger particle that's not going to move around as much. So all of those is tunable. It's quite safe. These lipids that are being used, these are derived from cell membranes. And so those are also very nice in that respect, that they're very compatible. The body has seen them throughout, and they can be used very nicely.
The next question is, what are the difficulties, challenges associated with designing a hydrogel or any matrix which can degrade over time and release multiple shots of vaccine at the planned time interval? Instead of visiting hospitals multiple times, one can receive one shot during infancy or whatever is the time period, and as the hydrogel degrades over time, the vaccine will be released as planned.
Yeah, so I think you answered the question there already. I mean, some of these systems can be designed. Now, how do you control the rate? It depends on what polymers you are using. It depends on what kind of trigger you are using. So maybe you have made this hydrogel in such a way that either these chains are degradable, and whatever is entrapped here, when these chains degrade, they come out. So in those cases, you'll get a release profile that maybe looks like this. This could be drug that is being released versus time. Now, if you want I think in your question it seems like you wanted also something that might be periodic, not continuous. So those would be a little difficult with the hydrogel, but you can mix and match couple of systems. So, for example, you can have particles encapsulated within a hydrogel, and maybe these particles release the drug at a certain time. So maybe these are like hollow particles, and this membrane is degrading slowly, so nothing is coming out till the membrane degrades, and once the membrane has opened up, all the drug immediately comes out. So you can have 3 or 4 different types of particle systems encapsulated here. So that's just one example. You can actually do a lot of several things depending on what you want to do. Maybe you want to just implant this and give the patient an enzyme, saying that whenever you want the drug to release, take this enzyme which specifically degrades the hydrogel, and that way you can only have the drug release when the enzyme is present. So there are various ways you can tune about. It just depends on what is the application, how practical it is, and how patient compliant it is.
Just a continuation of the same question. Even for COVID-19 vaccine, one injection for all the shots, why is this not feasible?
It is feasible. It is absolutely feasible. I think eventually people will go to that system. So I mean, of course, COVID-19 is a bit unique because suddenly it came out and people had no idea how to treat some of these things, how to develop vaccines, and there was urgent need because the whole world is kind of in a standstill. So people have tried out few things. In fact, there are like 50, 60, 50 to 100 different formulations currently in clinical trials. Now, 3 or 4 are already approved. Um, the, the the chances are that maybe one vaccination may not be good enough, and so most of the testing, the trials that are going on are with multiple administration, 2 or 3. But it may be possible that more subsequent testing may find out that only one is good enough, or maybe we want to make it much more immunogenic so that when that one shot is given, a lot of immune response gets activated, and that ends up becoming quite active. So all of this is possible. Yeah, I mean, I'm sure if the problem persists, more and more clinical trials will come up, and there would be vaccines that will be enough with a single shot as well.
So the next question is, how can we estimate the concentration of drug in the tumor site?
So this is tricky. I mean, of course, if you have to do in patients, it's much more tricky. You can technically, if your drug is, let's say, fluorescent or maybe radioactive or maybe has some contrast agent that picks up an ultrasound or maybe X-ray or whatever it might be, you could then do that, and that will give you some estimate of how much drug is there. But then in vivo, in humans, it's especially difficult because you have to worry about ethical concerns of being able to continuously sample the tumor space if you have to do injections and sampling out through needles and all. But then in animals, it's much more easier. You can modify your drug with fluorescent tracers or radioactive tracers, and do live imaging of the animal. You can euthanize the animal. You can take out the tumor space, sample it using various techniques such as HPLC or mass spec or whatever it might be. So those things are feasible and are actually routinely done.
I'll read a couple of questions from the YouTube now. So the first question is, the student wants to increase the bioavailability of a BCA class 4 antiviral drug, then among nano and microparticles, dendrimers, liposomes, micelles, which methodology should they use?
Okay, so let's see, bioavailability. So you want to increase the bioavailability of some antiviral drugs. Now it depends on several things here, right? I mean, the bioavailability might be quite high for the free drug itself. So so bioavailability is nothing but how much is actually available for action. So if let's say the drug is extremely soluble and you inject in the serum, then 100% of it's bioavailable. So you don't really need to use any of these systems that you mentioned. It'll be there anyways. But let's say, for example, the solubility of the drug is low, and you can't inject a whole lot of drug because it will precipitate in the serum and may cause clots leading to strokes or heart attack. Then in those cases, yes, you may need to use the systems. You can think about modifying it with polymers which are hydrophilic, so polymer drug conjugates. And then that way the solubility is high, so you can inject a lot more and it can slowly degrade and do whatever it needs to do. You can use any of these systems that you mentioned, and nano and microparticles, dendrimer, liposomes. Pretty much it depends on how the drug is. If the drug is only hydrophilic, then maybe liposomes are a good system because they do carry quite a lot of hydrophilic core. If the drug is hydrophobic, maybe you want to use hydrophobic polymers or micelles for that. So it basically depends on what is the drug and how long you want it as well. So if you want it for a very long duration, maybe you want a larger implant that you may want to inject. If you want it for short durations but longer than a free drug, then maybe liposomes might be a good system, or faster degrading nanoparticles, microparticles could be a good system. So all of that depends on these things.
I mean, as a continuation of the same thing, Dr. Kuman has mentioned that probably it is not possible to increase the bioavailability of a class 4 drug.
Okay.
So that's what she has stated.
Okay.
Okay. So we'll go to the next question. So the student wants to understand the concept of acetylcholine through liposomal drug delivery.
So it's very similar, right? I mean, so it's basically acetylcholine you can consider as a small molecule, acts on neurons and all. So now it is a fairly hydrophilic molecule, I believe. So if that is the case, then let's see, we can go back to our thing. So if it is a hydrophilic molecule, what you can do is you can prepare the liposomes. You can prepare the liposomes through the thin film lipid hydration method. And what you'll do there is you will take a flask, you'll dissolve your liposome in, let's say, chloroform, or not liposome, you'll dissolve your lipids in, let's say, chloroform. And then you eventually evaporate all this chloroform under some vacuum or some high temperature, so you get a thin layer of lipids here. And then you come in and add some buffer, and in this buffer you can then add your acetylcholine. So your drug can go here. So what will happen? These lipid films will come out, and because they don't really want to interact with water too much, they will form these vesicles. And as they are forming these vesicles, whatever drug is present in this region gets encapsulated in these regions, and that can then be used to inject and release this drug over time.
Now I'll take a question from which we had received in the forum. So the student is saying that in lecture drug delivery tissue engineering 1, a paper was discussed where heparin was used to bind to the bi-domain peptide and the growth factor was bound to that. She is wondering about what would happen to the heparin after the growth factor was released. Is the hydrogel biodegradable, bioerodible? And if the heparin is released into the blood, then will it affect the patient in a negative way because heparin is a blood thinner?
Yeah. So I mean, I think good question overall. The heparin by itself is actually a natural molecule, right? I mean, it's not like we don't have heparin; we have some heparin. So it will depend on what is the concentration. So this was an example from a research paper. They were using it on some animal model, and in this particular case, the hydrogels were erodible. So they can be degraded and eventually they'll go away. So heparin will be released. But then it depends on what is the concentration of heparin there. Compared to the whole body, the heparin concentration is generally very low in these systems. Plus, they are slowly degrading, so whatever heparin is being coming out on day 1 is already gone by the time the day 2, day 3 heparin is coming out. So, it generally is not a concern till you actually start to go beyond physiological concentrations. But yeah, if people do use a lot of heparin, then it could cause problems.
So the next question is again from YouTube. Please explain zero order elimination constant in case of ethanol.
Okay, so it's quite similar to like we discussed in there. So ethanol, now I don't know the values on the top of my head. I think it's about 10 ml per hour that it eliminates at. And so what basically it means that the ethanol which goes into your blood eventually goes to liver, and liver has metabolizing enzymes that break this alcohol or ethanol down at this rate. So about 10 ml per hour, and again this will vary depending on person to person. It's some people have a high metabolic rate, some people have low metabolic rate, so all of these will change on that basis. But it just means that because it's a zero order, that means it doesn't really depend on what is the concentration at that time. So you can have 100 ml of ethanol in your system, or you can have 50 ml of ethanol in your system. It will continue to be degraded at 10 ml, per hour, eliminated at 10 ml per hour. And so that's the whole concept here. So this rate is mostly governed by the liver, and since the liver is not really changing, so you can fill the liver completely with ethanol, or you may only have some, but then these enzymes are only limited, so more concentration does not mean that it'll get eliminated faster. Of course, some of this will also involve clearance through kidney, but that thing is less compared to the liver. The liver dominates the phenomena when it comes to ethanol, so it's negligible during that initial time frame.
Can we take a couple of numericals now?
Sure.
So one of the numericals, it's from the assignment itself. So consider a drug A that is loaded into two separate reservoirs
Okay.
whose drug releasing areas are in the ratio 2:1.
Okay, so the area 1 and area 2 is basically 2 by 1.
And the loading concentration of drugs are in the ratio 1:2.
Okay, so the concentration are in the ratio of 1:2, and we are looking at reservoir system.
Yeah.
Okay.
What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assuming that the reservoirs are flat and non-erodible, and the drug diffuses through a semi-permeable membrane in both cases.
Okay. Okay, so this is basically directly from the slides. You have your mass release at some point is proportional to the area of the device, and it's also proportional to the concentration. Now, most of the time, concentration is Cs, which is the solubility limit in the polymer, because again, in reservoir systems, you are loading quite a lot. So this question would need another assumption, which is basically that these concentrations, even though they are slightly varying, they are below the solubility limit, but they're not too low than the solubility limit. So if that is the case, then all you can do is simply say that okay, MT1 would be proportional to A1C1, whereas MT2 would be proportional to A2C2. So MT1 by MT2 is basically A1 by A2 multiplied by C1 by C2, and so that is nothing but 2 by 1 multiplied by 1 by 2, which is 1. So in this particular case, you will get that the ratio is 1 because they are equally releasing. There was another question on numerical.
Yeah. So the second question is.
Go ahead.
Yes. A core shell type nanoparticle is synthesized.
Okay.
The radius of the core is 2 nanometers, whereas that of the whole particle is 5 nanometers.
Okay.
What is the ratio of volumes of the core to shell?
Okay. So here's a core shell nanoparticle. The radius or the diameter?
This is the radius.
Okay, so this radius is given to be 2 nanometers. This radius is given to be 5 nanometers. And now they want to know the volume ratio of the core to volume ratio of the shell. So we know the so what would be the volume of the core? It's quite simple. It's a sphere, so it's 4 by 3 pi r cube, and r in this case is 2 nanometers. So let's say 2 cube. This is in nanometer cube. But we don't know the volume of the shell immediately, so let's see how we can find out. So what is the volume of the full thing? So the volume of the whole thing is again 4 by 3 pi r cube, in this case is 5 nanometer cube. So what would be the volume of shell? That will be nothing but core minus the total, or the total minus the core. So that is basically 4 by 3 pi 5 cube minus 2 cube. So this is what, 125 minus 2 cube is 8, and that will basically just become 113, no, 117. So that's what you'll get, and so this again will be nanometer cube. And so all you have to do is, now this is what we are saying is V shell. So you divide this number. So again, 4 by 3 by 4 by shell, right? So this will be 8 for the core divided by 4 by 3 by 117. So nanometer cube and nanometer cube, all of this will get cancelled and you'll end up with 8 by 170.
These were the two numerical questions that were asked. Now the next question is, what is the ex vivo method to check biodegradability of polymers?
So ex vivo method basically meaning you have to implant something and then take it out and then check how much it is degraded. So you can easily do that. You know how much you implanted, maybe by weight. So you can dry the thing before and after the implantation and take it out at various time points. And depending on, so maybe initially when you put it, it was 100 milligram. After 7 days, it became 80. After another 7 days, it became 60. So you know that every week it is degrading by 20 milligram or so. So these are some of the methods you could use. Again, you can also use fluorescence here if you don't want to euthanize the animal. You could just simply continue to track the amount of fluorescence you're getting from the implant, and that will tell you how much of the fluorescence is left, proportional, which is proportional to how much of the implant is left.
So next question is.
So there are some questions in the middle that are remaining. Maybe we can take them, otherwise they'll scroll up.
We have taken those.
The exam thing?
Yeah, exam thing. Okay. Okay, so regarding the exams, we have these questions like what will be the total number of questions and time duration of the examination?
Okay, so the total number of questions will be about 50. There'll be 35 MCQs, multiple choice questions, and there'll be about 15 numerical type questions in which you'll have to solve and just fill in the blanks type thing. A range would be, you'll get an answer and your answer should be within that range for it to be correct. So yeah, so 35 of multiple choice questions and 15 of those. In terms of time duration, I believe it's 3 hours, if I'm not wrong. You can check. I think this is all this information is present on the website of NPTEL. I think it is 3 hours, but you can check that on the website.
Also questions like marks division for the questions and all.
Yeah, so those will be there. I think MCQs would be of lower points and numericals will be of higher points. I believe MCQs have 1 or 2 points and double for the numericals. But again, some of these formats are given, and you can also ask this in the forum, and we can tell you them as well.
Yeah. So the one of the questions from the YouTube link is, please explain the reason for cytokine storm in our body.
Okay. The cytokine storm is basically meaning that your immune system is going berserk. It is secreting lots and lots of proteins, chemokines, and cytokines. And this could be due to several reasons. Maybe there is a very high load of pathogen. So what happens is each pathogen goes and maybe activates 5-6 different cells in the surrounding because it's shedding out some PAMs and some proteins that the immune system doesn't like. And so if that is the case, then now suddenly if you have 10 to the power 8 pathogens, that means now 5 into 10 to the power 8 immune cells are getting activated. I mean, this is just a crude analysis I'm saying. But so if you have a very high load or if you suddenly your immune system is getting activated, and we know it's a cascade event, so one will activate 5 will activate 25, and so on and so forth. And so eventually it may come to a point where there's so much cytokines that pretty much all of your blood vessels are getting dilated, you're not getting enough blood transport to happen, oxygen is becoming reduced, immune system is taking a lot of energy, so all of those side effects will start to then come in.
So the next question is from one of the forum questions. So to reduce complement activation, one of the methods that was suggested is to make surface less nucleophilic. that is to reduce the negative charge of the surface. So we in one of the questions for in the assignment we had said that the option is to reduce surface electrophiles also. So the student is saying that that should also hold true, as it is also an approach to reduce complement activation as the reducing as it is also reducing the electrophiles in the surface on the surface. So what do you think?
So the original question was what was the major thing that was being asked?
So to reduce the complement activation on the surface,
What are the strategies?
What are the strategies? We
Okay.
had given the options as to make the surface less nucleophilic and also as electrophilic. So does the option both of the options do they match in?
No, so not really, right? Because if they are electrophilic, then they are electron loving.
So it's the option was to reduce surface electrophiles. That's
I see. Yeah, technically speaking, that could be correct. We could look into that.
Yeah.
Yeah.
Um, yeah. Regarding the questions, this is all what I had.
Okay.
We had some questions related to how we get into PhD.
Yeah, I think there's a couple here also. This
Okay.
thermal ablation.
Yeah.
Nihil
Next
is,
question is, please tell about the thermal ablation technique.
Yeah, so I mean thermal ablations. I mean these are basically you're giving in some heat to either reduce the tumor size or maybe some area where you want more inflammation to happen, you want more blood flow to happen. So when this is done, I mean this is mainly a medical thing. You could read more about it, but yeah, I mean in a nutshell, it's basically giving some heat energy to either kill some cells or increase the blood flow in that area.
Probably this is all
Okay.
the questions that we have for the session right now. We also have, in general, many people asking about how to do PhD under you or how to do PhD in the department. And
Sure, sure. I mean that's not really a part of the NPTEL course, but in a nutshell, if I want to say, you feel free to email me. My email, there's a website. I think one of the person is also asking my email ID. It's also shared in these NPTEL slides. So I think in the last lecture, you'll see that. It's rachid@isc.ac.in, and yeah, feel free to email me for PhD. We have ISC has its own central portal in which you have to apply, and then there you can choose bioengineering as a subject, which can then be which if you are then shortlisted, you'll be called for interview, and then if you make it to the interview, you'll be offered PhD in our department. Yeah.
Also, people have been asking about how to prepare for the exam and the numericals. Do you have any?
Yeah, I mean, there's nothing really beyond to what you have been doing for the assignments. It's quite similar to that. And don't stress too much with the exam. If your concepts are clear, the questions are mostly conceptual. There'll be some memory part, of course, that will be involved, but the more focus on the exams, especially the numericals, would be on the concepts. In fact, most of the equations will be given to you, so you don't even have to remember the equation, and all you have to do is just apply them. So you don't stress too much. They'll be very similar to the way the assignment questions were, and you can just use them as a practice for the final exam. I guess this when this course will be offered next time. So this is offered every year. So this will be offered next fall. This time the cycles were a bit shifted due to COVID, but then I believe it starts in July again in 2021. And yeah, thanks to all of you for wonderful comments here. Well appreciated, and very good luck with the exams. Don't stress too much. I'm sure you'll all do well.
And we also request you to please provide the feedback for our.
Yes. After the course, I think there'll be a feedback form sent by the NPTEL. So do provide comments there if there are some things we can do to make the course even better. Okay. Thank you all.